Timer starts now.
Yes. Okay. Hello, everyone. Thank you so much for your time. We will be presenting problem 14, ice clock, for string beam theorists, which is UC Berkeley. My name is Shantanu Kadam. Vivian.
Hi, my name is Siddhant.
And so let's start off with the prompt and identifying the key parameters of the prompt. So first of all, the prompt says an ice cube inside a mix of vegetable oil and baby oil will remain between the two liquids because of its density. As the ice cube melts and releases trapped bubbles, it goes up and down periodically in an intriguing way. We have some pictures illustrating this dynamic in the next couple of slides, along with an explanation theoretically of what's going on. But there's another part of this prompt, which is where we get into the key parameters. The first part is, can this experiment be turned into a clock? What would be its longevity and precision? So there's three things here. Can it be turned into a clock? What is the longevity? So longevity is really like the duration in seconds for this ticking, if you will, of the clock. And then what is the precision? So the precision we've associated with the period. So those are the three key kind of, those are the two key parameters that we've chosen for part one. And then part two is the other driving part of this problem, which is optimize the setup parameters, such as shape, temperature, composition, length scales, etc., to obtain the maximal clock precision. So there's two things here. We chose to fixate on shape, temperature, and composition as the setup parameters. And then we were looking at maximal clock precision, and we interpreted that as being a 60-second cycle, where a cycle is defined as the amount of time for the ice to oscillate through one time. So Vivian's going to tell us more about what that means qualitatively from a theory perspective.
Yeah. If we first drop the ice into the oils, which means the ice lies in between two oils, and I measure the density for vegetable oil and baby oil. Basically, I measure the mass and volume and calculated the density. So the density for vegetable oil is 0.93 gram per milliliter, and the density for baby oil is 0.83 gram per milliliter. And we all know that the ice density is 0.9, so the ice will float between these two oils. And we can see from this free body diagram, the baby oil is providing a downward force on the ice, and the vegetable oil is providing an upward force in the ice. And in this case, it reaches an equilibrium, which Shani can go back to the previous slide. I still have one thing to explain. Yeah, and we can see the picture on the left. Now the scale is at 6.5, which is the original position. Yeah, can you go to the next slide? Thank you. And so because of the temperature difference, the ice will melt. And we all know that the water density is 1, so which is greater than the vegetable oil density. So the water drop will sink. However, the water is still contacting with the cube. So there is a dragging force provided by the water, which is downwards. So the dragging force together with the cube and the force provided by the baby oil will drag the thing down, because the water acts as a trigger here to pull the ice down. You can see very clearly from this free body diagram. And we can now see from the picture on the right, the scale now is at 5.8. Okay, so when the water leaves the ice will float up because it is now surrounded by only vegetable oil. So it will only feel a force going upward. So the net force is going up, so the ice cube will going up. And we can see from the picture, at the instant the water drop leaves the ice, the scale turned to 5.995. And finally, the cube will return to its original position, which is again in between the two oil, the starting equilibrium. And we can see from the picture on the left, it's at 6.5, the scale.
So now that we've talked about qualitatively what's going on, let's talk about what this up and down means. You know, Vivian has explained how we consider that to be a cycle, right? From when the ice starts at a position, goes down, bounces up, and comes back to that position, which, as we saw in the previous pictures, was like 6.5. That was one setting. So that cycling kind of implies that maybe there's some sort of oscillation happening here. And in fact, if we had something like simple harmonic oscillation, that would really click with this idea of using the ice as a clock, right? So let's look at what simple harmonic oscillation might look like if we looked at just a single cycle. So we know that the equation for simple harmonic oscillation is A sine omega t. Here, d is the displacement, and we have it as a function of t and omega because we'll measure the displacement and we'll know the time. So we'll be calculating omega and a, which is the amplitude. And yeah, so using f equals omega over 2 pi, as well as t, so f is frequency, and omega is angular frequency, and t being the period, t equals to 1 over f, or frequency, we have a relation between omega, angular frequency, and period. And then from that, we can rewrite displacement for simple harmonic oscillation in terms of the period. And the period is what we're looking at when we're talking about the cycle here. And so again, remember, we define maximal precision to be having a period of 1 minute. So that's why t equals 60 seconds here. And so this will be useful when we get some data out of our experimental setup and actually do some curve fitting with it. And back to Vivian.
Oh yeah, so sorry. Oh yeah, so I'm now going to talk about optimal setups. We change shape, temperature, and composition. So the expectation when we change temperature, we think the oscillation will be faster because as the temperature goes up, the ice will melt faster, so the period will decrease, so the oscillation will be faster. And the expectation when changing shape, we think that the time when water and ice is getting contact with each other may change as the shape changes because they're having different configuration. As shown in the picture I drew here, the sharper the corner is, the quicker the water drop will leave the ice because it's harder to maintain the drop at the sharper corner as it follows the tendency to drop. And the expectation when changing composition. So there are basically three cases. The first one is having both oils density less than 0.9, so the ice will just simply sink. The second case is having both oil with density greater than 0.9, so the ice will float at the surface of the liquid, and the cube will stay still on the surface while dropping the water down, because the downwards force provided by the water will not be large enough to balance with the upwards force provided by the oil. The ice may sink a bit, but it will still float on the surface. And on the case of the oil with one with density between 0.9 and 1 and the other one with density less than 0.9, it gets complicated if we want to maximize displacement.
And just as a reminder, the 0.9 is how we measured the density of the ice.
And we can see the picture here. First, let's talk about the second oil because it's simpler. So if we want to maximize the second oil, the density of the second oil, minimize the density of the second oil, so the force provided by the second oil will increase because the difference between the density of the oil and ice increase. So it will travel more distance, the ice. But however, it cannot be too small because if it's too small, there will not be enough upwards force provided by the first oil to balance it in the first place. If you are changing the first oil, if it gets close to 1, the force provided by water drop will decrease because of density difference decrease, and the force provided by the first oil upwards will increase. However, if it gets too close to 1, the oscillation may not happen because as I said before, the force provided by water is a trigger. So if that trigger is too small, the oscillation may not be very obvious. So now I'm going to talk about the experimental setup. So I took a picture of my experimental setup, and I used it. And you can see like this is a cup with scale, and the baby oil is at the top, and the vegetable oil is at the bottom, and ice is in between. And I have a ruler measuring the displacement of the ice.
And we use this type of setup to answer both parts of the question, the clock, as well as the optimal setup.
Yeah, and this is a setup for my temperature, changing temperature. This is changing shape.
So notice for the changing shape that we use different ice molds, one with the trapezoid, one with the cube, and one with the sphere. And you'll actually see those results in just a second.
Yeah, and I also changed the composition with the first two cases as I discussed above.
With olive oil and vegetable oil. All right, so here's one of the coup de grace. Here we have the data analysis where we measured the displacement for a cube, and then we came back to that cube 34 minutes later using the setup and the pictures that you saw, those types of pictures. We fitted using this formula here where we took the simple harmonic motion, but with displacements, and we found several things. The most important is that we can engineer a period of 56-ish, 50 plus or minus 6 seconds. And that leads to the answer that the phenomenon can be used into a clock where we can tune the precision and longevity for over 36 seconds, leading to this idea that the optimal setup can happen if we have this certain type of, oh, I'm sorry, I'm going the wrong way. Sorry. Oh my goodness, I'm so sorry. The optimal setup can happen if we use a 21.7 degrees Celsius temperature setting at the beginning of the experiment with a cube shape and try to increase the temperature only slightly, not enough for the density of the oil to decrease. And these are some future considerations that we had that going forward we'd like to work on. And I think, is our time up? I didn't hear anything. But...
Oh, I'm muted. I'm sorry. Oh, I was talking to you. I'm so sorry. And thanks for the reporters for their presentation. So, do the opponent have any clarifying questions?
Who is the opposer?
It's Bowen.
I'm opposing.
Okay.
Yeah. So there are several questions that I like to ask. The first one is that we noticed that you said you controlled the temperature as a control factor to see how it works. But I noticed that when the ice inside the bottle melts, it actually absorbs heat from the oil. So the temperature of the oil is actually decreasing, right? So does that affect your results? Because it's actually melting slower and slower inside the oil. And another one is that we see that the water thing drops down to the bottom of the oil, and that makes some push-ups to the oil maybe. And that makes every time when the ice comes back to the equilibrium position, it might not be at the same distance. You get what I mean? Like it goes from bottom to, like, it was originally here, and since it was pushed up a little bit, and the ice just goes another way around.
Can you say which question you want us to answer first?
The temperature one, please.
Okay.
So sorry.
Go ahead, Vivian, please.
So for the experiment result of the temperature, Shantanu can go to the results slide for the temperature. I was gonna say, like, we actually failed doing the experiment because when the temperature goes up, the ice cube, it just sinks to bottom, like nothing happens. And the reason we given to that is just is because when the temperature goes up, the oil density will decrease. So when it drops to down to the when it drops to less than 0.9, the ice will just sink to the bottom.
No, my question is like the temperature of the oil might affect how the ice melts.
The time is up for this part, so let's move on. So the opponent, you have 3 minutes to prepare your presentation. I'll start a timer and have you have a 1 minute warning for you. Okay, the opponent, your time is up.
Yep.
You can start sharing your screen and start the
Sure.
presentation.
So can I ask my teammate to like put the slide on? Yeah, thank you, Riley. All right, so let's go. Yep. So firstly, thanks for presenting, and it's a very nice lab, and we got very much explanation in it, and also it goes from theoretical to practical, and the data collection is very good. And also the fitting is very intriguing. Like you can really see the sinusoidal shape inside their data. So I think that's a very good thing. And also the variables are controlled and varied in a very good manner. And next slide. And I think the environment controlled in this lab is temperature, shape, and compositions. And one flaw, I mean, like something I like to add on is the temperature of the oil, like the system actually changes. So that could be something to improve, I guess. And also we got why it happens. And also we got the time period varies due to some reasons. And yeah, maybe we need a reservoir like to maintain the temperature of the oil, like when so that when the ice melts, it doesn't change the whole temperature of the oil thing. Yeah, and next slide, please. And yeah, though the lab is very good, there's something to like think about. So every time when we see the formula, the d equal to sine some stuff, we're thinking that the distance, that d, might not stay the same every time because of the air flows, or say the water drops to the bottom and pushes up the oil, things like that. And also the temperature of the oil is not kept as a constant. That's what I'm talking about, like over and over again. And also the surface tension on the ice block is not negligible, I think. So are there any factors that could like, is it a factor that could affect the precision of this clock? Because the surface tension might push the ice, in the oil. So that's a factor to consider. And also the shape of the boundary between the two oils, is that a flat thing? Is that a flat plane, or is like something flagged around? I don't know. And I think it would be good if you mention it. And yeah, the last thing is very interesting question. Like the different period have different precisions. Is that true, or like every period have the same precisions? Because if it have different precisions, you can you could go to the next. Yeah, if it has different precisions, you can like increase or decrease the period to change the precisions. And also, what we like to see in more of the report. So firstly, we know that the ice can be frozen in different methods, so there's less air in the ice. That is to change the density of the ice, because normally when we put water and just put it into the fridge, you get ice with very much air in it, and it is very less dense. So maybe that could help with the temperature, I'm thinking. So if you get like less air in the ice or more air in the ice, you could maybe help with the temperature factor experiments, that one. And also there's very few error analysis in this lab. So probably if you could do some error analysis, like including uncertainties and see if it agrees with the experiment outcomes or not, that would be cool. But that's some statistical stuff to do. So some suggestions that we're thinking about. So firstly, if the ice has some impurities inside it, what would that affect the lifetime of the clock? Say if there's like some dust or some other things going into the ice, what would that affect the lab? And also the actual density of the ice measurement could be more helpful so that you can choose like a better composition of oils. Yeah, next, please.
You have 5
So
seconds.
you have next. That's it. Okay.
Great. Thank the opponent for the presentation. So now we are going to have the reporters and opposer to talk about the questions just raised. And you have 5 minutes. Time starts now.
Yeah. So I'm sure Vivian also would like to say some stuff about this conversation. But first thing is, I wanted to start on the point you said about the displacement, the equilibrium position perhaps being different as water melts off the ice as it drops to the bottom. I agree that can be a factor, especially if you're measuring over several cycles, like for over like 10 minutes or 20 minutes or something.
Yep.
And in that case, what we would do is we'd use the same approach. And this is something we would like to do moving forward with this problem. In order to really expand upon like what is the longevity, right? Like how long does the clock actually last? But what we would do is we still expect there to be a roughly sinusoidal or harmonic type of motion, but perhaps it decreases over time, right? So maybe there's a linear or quadratic combination going on there with some other function, which would not be very difficult to figure out. Or perhaps also it's worth considering is there a damp harmonic oscillation? And that is something we wanted to implement, but we thought it would be better to start with the simple harmonic case, right? Start with the simplest case and then build our way up from there. So we started with the simple case and then we said, okay, now what are some other factors we can measure? And that's when we started talking about what is the optimal setup, temperature, composition of the ice, etc. And one other comment I will make, and I think Vivian might have something to say about this or one of the other topics, is that in terms of composition of the oil, we did consider that. And I know Vivian can talk more about composition of oil than I can because she looked a lot at the densities. So maybe Vivian, do you want to talk about it?
Yeah, sure. So wait, Shani, so the what do you mean by so the density of the oil, like what exactly you want me to say?
Well, so I think, Bowen, you were saying that in addition to considering density of oil, we should consider density of the ice. Is that correct?
Correct.
Right. So Vivian and I discussed that.
Oh yeah, so basically we think it's the difference of the density that matters, that which leads to the ice to oscillate. Because I do agree that we need to measure the density of the ice, and I think it is kind of flawed if we just assume it's 0.9. However, if we measure the density of the ice, we think the result will not like will change, but it will like, because it's only the difference that matters. So the result will not. So our model still fits, you know.
And one other consequence of that is we approached it as the difference matters. So let us consider changing the oils. But you bring up a good point, which is that we could also consider changing the ice, and perhaps we'd have more success. Because as Vivian mentioned, when we started to heat up the oil, we weren't able to heat it up successfully without it disrupting the equilibrium and oscillation of the ice cube.
Yeah.
One thing we did want to say about the temperature of the bath changing is I think your idea of the reservoir is very interesting, but one thing that we noticed, and Vivian did a lot of the experience, so she can probably talk more about it. But one thing we noticed was that there was much more oil required than there was ice, the volume. And so therefore, over the time span that we were measuring, the temperature did not change significantly. I was curious, did you perhaps do the experiment and like actually measure the temperature? Is that why you're asking about the change of the overall system?
No, I'm just thinking about what factors could affect it, and it seems to me that the ice could absorb a lot of heat.
I mean, did you notice the temperature changing over time, Vivian?
I didn't quite measure the temperature, but I do notice that the ice damped as the temperature as the time goes on. So basically the period of the oscillation increased. So I think that may have something to do with the temperature. Because temperature goes down, that's why the oscillation decrease.
What were the other things that you wanted to discuss?
The precision one, the period and precision, are they correlated or not? That's what I very want to know. Yeah.
Or if we set the clock to have a given period, does that influence the precision? That's the question, right?
Seems so. Like, are they correlate? Like the longer period gave smaller precision, or smaller period gives longer precision, something like that.
Yeah, so
Is there any study about that?
the way we define precision was as the period, right? So we said the closer we can get it to 60 seconds, the better, because we were thinking of time and a clock. So I guess literally for us in our interpretation, like that's how we felt justified defining the period for the experimental data we collected. And so that way, I guess the direct answer is as you increase period, you also increase, as long as you're increasing period up to 60, you're increasing precision, but then after that, you're decreasing.
Okay,
Yeah, I see.
from this point on, all the team members are welcome to make any comments. You still have 5 minutes to discuss.
So I wanted to kind of do you the courtesy that I did, you did me. So I was wondering what else you had left to present before you ran out of time.
We did get through everything. The last few
Oh, you
slides
did?
were a little
Okay.
rushed.
Okay, cool.
Thank you, Liam. We do appreciate that. We did get through everything. The last two slides were a little rushed.
Okay. Sorry. I know I'm a judge and I don't want to intervene this, but it would be helpful for us judges if we could actually see the results slide one last time, because it was pretty rushed, and just speaking on behalf of the judges, we weren't even able to finish looking at it before the presentation.
And for judges, you will have time to ask questions, but if the teams would want to pull up that slide, they feel free to.
And yeah, if you have the results, I also have questions about error. So
I did have one question for particularly the opposer, or like anyone on the opposing team, and also my team can also chime in. But it's like on the issue of the boundary layer, and it was kind of brought up by the opposer, like what would happen? Would you expect there to be any difference between two miscible liquids? So you have like a continuous transition between oil 1 and oil 2, or what would happen if you have like a discrete transition where like the two fluids are not miscible? I was wondering whether you had anything or any ideas.
Okay.
I feel like the characteristic period would change, because I think the the point, the mass, the critical mass where the liquefied water drops off, I think the critical force it has to go to separate and go into a denser layer, that since it would be continuous, I would assume that it wouldn't be such an instant process,
Oh, okay. So basically what you're saying, just to like recap, what you're saying is that in the case of a continuous boundary layer, what we're going to observe is that the ice, as it moves down, is going to move down like in a different manner. So like in the case of a discrete boundary layer, we're going to have something more akin to a very precipitous drop and a very precipitous rebound back up, simply because there is, okay, yes.
I think it would go quicker, and I think it would be more continuous. Yeah, that's a really interesting question, though.
I actually did have a follow-up question for the presenters. So the process that you did, was it like a continuous one or like a discrete one? Because in one of the YouTube videos that was linked to the question, it was the ice was usually going at the different positions in increments, and it was not a continuous process. So is there like a quanta at which only we can measure time, and not smaller than that?
Yes, and Vivian kind of hit that on the head with the way that we defined the precision or the optimal timekeeping, which is the smallest quanta is 1 cycle, the amount of time it takes for 1 drop of water to form and drop off, and for the ice cube to bob down and bob back to its resting position, which, as Bowen pointed out, may shift over time. But like just from one to the next. So every time there's a drop of water, that can be considered as marking 1 quanta.
Oh, okay, that's interesting. Okay, so, and also about your data. So I see, can you just go to the data collection slide? That's awesome.
Yeah.
Right, so I was just noticing in this data that do you think that this was like in a way a sufficient amount of data? Because to form a sinusoidal wave, you usually need like a whole cycle of it, and this seemed like a parabolic function could also fit this data, or like some sort of polynomial function. How did you come about that?
Yeah, that's an excellent question, and I'm really glad you asked that. So when we looked at this, we actually started kind of with the question that you asked us, Adit, which is what is the smallest quanta we can look at? What is the smallest time scale? Because in our mind, it's like, okay, if we want to see holding as much constant as possible, right? Trying not to think about displacement shifting over time or dampening force. If we look at one cycle, what does that behavior kind of look like? So the simplest case possible. And so we literally just collected enough data to see one drop form and bounce off, to see that one segment. And we did that several times. So that's what you see here with different shapes. And so to answer your question, this is not sufficient to say in any decisive manner that the motion is indeed harmonic, but it is adequate to say that the motion could be harmonic, and there is incentive for that. So moving forward, one thing that we look forward to doing is actually measuring for several cycles in order to really get the second end of the curve. What you can see on these, oh, sorry.
Your time is up, and it's time for us to have you to have some closing remarks.
Okay.
That's 1 minute.
Yeah, so I guess to close, we will, well, okay. So closing remarks. The problem has to do with the cycling of an ice cube in, or an piece of ice in two different densities of oil. And this type of phenomenon we do find through our research can be used as a clock, as a timekeeping device, where we've defined longevity in terms and precision in terms of 1 minute. And this is a very basic assumption/model, which has a lot of room for development, which the opposing team has rightfully pointed out in terms of displacement and possibly temperature, as well as measuring over several cycles. And so we're really excited to take this groundwork, which seems to have some initial success, and really expound upon it to really flesh out some of these answers. And the other aspect is we did answer the second part of the problem, which is what is the optimal setup? And we did rush through this, so I'll briefly pull it up. But we find the optimal setup, if you want to go 60 seconds, is to use an ice cube, not a sphere or a trapezoid, at a specific degree of the system. And so we did answer both parts of the question.
Thank the reporters for their remarks. And now it's time for a jury to ask questions. So judges, do you have any questions to ask reporters or opponents?